Hello everyone and welcome to another Würth Elektronik ISOS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is EMC Filters from Component to Design. Our speaker today is Ismael Molina Alba, who is working as Senior Product Manager in the field of EMC inductors and RF components at Würth Elektronik ISOS. He will hold today's webinar and also answer your questions. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but are holding the webinar out of the home office. In case of technical problems, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at isos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will receive the link to the presentation as well as to the recording of the webinar only in the next few weeks, as we need a little longer processing time due to the extended webinar offer. So now I will hand over to our speaker Ismael, and I wish you an exciting webinar.
Hello everybody and welcome to our training or contactless training or home office webinar. So during our webinar today we will be talking or making a small introduction. So why we are starting on what was the motivation to start this training. Later on we will talk about the need for filters and the different topologies we can find. Going through the components and technologies we are using to build a complete EMC filter. How should we choose a component for a filter, going through all the features and the information we can find on the data sheets and all the relevant information that we need to discover. And finally, we'll go on how to destroy a filter, and not really destroying the filter, but pointing out what are the main issues we can find when we build a filter and the filter is not working like we expected. Let's start with the introduction. So this is a case we had from some customers, where they were pointing out that the filter wasn't working like they expected. So when we received the information from the customer, we saw that what they have in the application was an inlet socket where they have the input in the circuit. Then from this input was the mains line was going to a switch to switch on or off the circuit. Then from this switch, we were going to the filter, and from the filter to the AC, DC, and DC-DC converters in our equipment. So what we can see here as evident, because I made the schematic very simple, so there were more components into this board, is this that now we have some kind of inductive coupling in the circuit, creating basically a noise path for our for the noise to go back to the mains line. So basically what we saw from the customer, or the picture we received, was the radiation, or the conducted emissions. And what we see detailed in the picture is that we have the harmonics at the different frequencies here, basically at 210, 320, 430 kilohertz. So what we can imagine is the customer had a DC-DC converter with a switching frequency of around 105 or 100 kilohertz. So the problem wasn't that the filter wasn't working. The problem basically was the location of the filter. So we were creating a low impedance path parallel to the filter, which has a high impedance. And our signal will be looking always for the less effort path. So the signal, or the noise in this case, was looking for the lowest impedance. And this was through some inductive coupling through the cables we had inside the system. So basically what I want to say with this is filter is no magic. When we have a filter, we have basically some different passive component put all together with some potting material, probably in some case, metal case, and we need to know how to use it and what are the right parameters we need to consider, not only for the filter, but for our application to make it work. And this is what we will be talking today during this training, during this webinar. The need for filters and topologies are basically coming from the conducted interference we have. So we have two range of frequencies where we are looking at different emissions, different kind of mediums to transmit these emissions. So between 150 and 30 megahertz, we are looking at the conducted interference, where we take a look to our cables. Over the 30 megahertz, we start looking to the radiated interference. And why is that? So it is not like we expect to have other sources. It could be that we have different sources for this noise, depending if we are radiating or if we are conducting. But we could have exactly the same source of the noise, but depending on the frequency or the harmonics we have, it gets easier for our circuit to start radiating. So we will be designing some antennas, some unintended antennas in our system, where they will be emitting above these 30 megahertz. To have a good efficient antenna below the 30 megahertz, we need cables and traces really long, which is almost impossible to have in our circuit. When we take a look to an EMI filter, we find this is a basic example of an EMI filter, and we have basically in this construct, we have one common mode choke, we have two differential mode chokes, we have also two X capacitors and two Y capacitors. But while designing a filter, we put a bunch of components together, but we need to know what are they filtering. So basically, we need to build the different models of our filter. So one of the models will be the differential mode model of our filter. So in this case, we have the biggest effect on the differential mode will be coming from the differential mode chokes, the X capacitor. So we have a little influence of the Y capacitors, and we have almost no influence from the common mode choke, as our common mode choke will be only apporting to the differential mode the leakage inductance, which is really small in comparison with the nominal inductance. On the other hand, we have also the common mode model of our filter, and here we see that the X capacitors completely disappear from our system, and now we have a reduced effect from the differential mode filter, and we have the full effect of the common mode choke. So we basically have here the full inductance and losses of our filter. And of course, we have a bigger influence of the Y capacitor, which are the capacitor which will be having the main influence in our common mode filter. So once we talk about the components we have, something we have to consider is that the placement of the components is also really important and relevant for our filter and the efficiency we will be seeing in our filter. So in this case, we have different orders of filters. So we have from order 1 to order 3, which means we have 3 or 1 reactive component. And depending if we have a high impedance or a low impedance in the line, we will increase the efficiency of our filter with starting with a low impedance, which would be a capacitor, or starting with a high impedance, which means an inductor. Why is that? Well, when we are filtering, we are not only filtering with the dissipation. So we are not only creating heat inside of our chokes, inside of our filter, but we are also reflecting the signal. So basically here we are doing the opposite, like what we do for our antenna. So when we have an antenna, we try to match this antenna to the best, to the impedance of the line. So we reduce the reflections. Therefore, we get the maximum signal to the antenna. In this case, we try to have a big mismatch, as we will try to reflect also part of the noise. So our target is not only to dissipate, but to avoid the noise to get into our circuit or out of our circuit. So of course, we talk here about the order. So depending on the number of reactive components we will have also a different effect of the filter. So if we have 2 components, we have 20, if we have 1 component, 1 reactive components, we will have 20 dBs per decade of attenuation. And if we increase the number of components, we multiply this dBs per decade. So having 2 components meet 40 dBs per decade. So increasing at the end the attenuation we have in the rejection band. And of course, like I said, it's not only the rejection band or the slope we get with the components, but if we are filtering also through reflection or dissipation with our filter. So the components and technologies we are using, when we talk about components, we can start talking about the common mode filters. So these are in EMC the central component of our filter. And why is that? That we will see in the following slides. So when we have some conducted interference, usually this interference will be in common mode, as our signal will be always transmitted in differential mode. So the main interference we may have will be some common mode currents. So to solve this situation, we may include a common mode choke in our circuit. Including this common mode choke, we will reduce the common mode currents in the system, reducing also the radiated interference. Important to know why we are affecting only the common mode and not the differential mode is we need to understand also the structure of the choke. So when we take a look to a common mode choke, we see that we have full symmetry between both lines. So basically we have, if we place a mirror in the middle of our common mode choke, if we place a mirror here, we will see that we have exactly the same 2 halves of our in the component. So this is leading us to have a perfect compensation of the field, of the flux, of the magnetic flux inside the core. So basically, when we have a differential mode signal, we have the same signal. We have the same signal with opposite phase. So we have 180 degrees phase difference, which means opposite direction of the signal, same magnitude. With this opposite direction of the signal, we basically create the same magnitude of magnetic flux inside the core, but with completely opposite direction or opposite phase. This will lead to a compensation of the magnetic flux inside the core, and this compensation of the magnetic flux creates or is not magnetizing our ferromagnetic core, which creates no inductance of the component. And no inductance created means we have no impedance in the line, so we are not dissipating or reflecting any energy of our differential mode signal. Therefore, we let the complete signal, if we were in an ideal world, going through the component. When we talk about the common mode effect of the choke In this case, we don't have opposite direction, but we have the same magnitude and same phase of the signals in both lines. That will lead to have the exact same magnitude and phase of the magnetic flux inside the core. This will create a magnetization of the core, therefore creating an inductance, which will generate an impedance in the line, and this impedance will dissipate a portion of the signal, will dissipate or reflect. At the end, we have less signal at the output of the choke. This is why the common mode choke is the main component or the central component in our filters, as we get, I would say, a smart component, which make a differentiation between differential mode and common mode. Here we have a small simulation. I will skip really fast through this. This is just to see what we are when we create a current in a winding which we wound in a core. We will be creating a magnetic field, and this magnetic field will be in one direction on the core. If we take a look also to the same simulation but with differential mode, in this case, you can see here on the right, you can see the component we are basically simulating. We make a cut in the middle of the component, and then we take a look to the magnetic field we have in both sides. So in this case, we have opposite direction of the currents. So we have differential mode, same magnitude. With this differential mode, we see there is almost no magnetic flux inside. We create, though, some asymmetries in the simulation. So we told our simulation software that we should create some asymmetries in the windings. So we have a 99.9% of symmetry in our choke. And this is leading, if we zoom in into our simulation, if we zoom in into our simulation, we will see that we have some magnetic flux actually on the choke, on the core. This magnetic flux is the one which is causing basically the leakage inductance, and this leakage inductance is the one generating some impedance in the line in differential mode. That's why we don't have ideal component, we have real component which has some asymmetries. So therefore, we can see two effects. When we talk about the impedance created on the line, we can consider that we have the impedance of the winding and the parameters of the core material. So the core material had some losses and some capacity to conduct the magnetic flux. So basically, the real part of the permeability is the capacity of the core to conduct this magnetic flux, and the imaginary part are the losses we will have. So when we take a look to both graphs, we can see one looks really like the inductance over frequency, and the other one looks like the losses we are generating in our circuit. So going to the next slides, we can see here, or what you can see here is the graph we have in our catalog. So you can find this on the first page, where we explain, or we try to explain a little bit the effect of different core materials. So here we start with iron powder. So we can see the iron powder inductance is dropping really early on frequency. So which means we are losing these properties of the ferromagnetic material, or of conducting the magnetic flux. The same, or the mangan zinc is a material we use for middle frequency, so we see the inductance is also dropping later on in the frequency, and at the highest frequency material is the nickel zinc. So in this case, you see basically what we are representing is the mu prime, so the permeability, the real part of the permeability. On the other side, if we start talking about chokes and not inductors, power inductors, you will be able to see that basically our curve is starting when the other was ending. So now we are showing the impedance, and the main parameter which is creating this impedance is, in a lossy material, are the losses of the core. So in this case, we have different materials with different losses, and these losses correspond to the imaginary part of the permeability of the core. What am I saying that? So what I'm telling you that is when we talk about power inductors, we usually said that we should stay 1 decade before the resonant frequency, so we are not having so much losses on the core. And this is coming directly from this graph you have here. So basically, here are my losses. And when I'm talking about power inductors, we usually tell the customer to use the power inductors in this frequency range. So we are as far as possible from starting having some losses. If we increase the losses, we reduce the efficiency of our, for example, DC-DC converter. In the case of chokes, what we have is we have the signal, the power or the data signal is usually in this frequency. And we want to have the impedance, or what we are doing is we are using the common mode choke for filtering in this frequency range. So our differential signal due to the field compensation could be anywhere because we have almost no effect of the core. Remember, we have no inductance, while we try to have as much losses as possible for the common mode. And this is mainly the secret. This is why we are taking a look to the losses and not to the inductance or the capacity to conduct the flux of our cores. And this is why the guys building common mode chokes are taking basically the core materials that the guys from power doesn't want to use, because for us, the highest the losses, the better. When we talk about the winding styles and the effect of the different winding styles, we can check really easily what is the effect of both styles. One is the sectional. Basically, we have a separated winding. They are both separated. They are both separated totally, one from another. And the bifilar winding, we have both wounded together. So we can imagine the symmetry we have in the bifilar winding is much higher than the sectional one. Here we can see the example with one of our chokes. This is the SL2 series. And here we have two components, one with bifilar, the one without S, and one with sectional winding, the one with S. So S is for sectional. So basically we have the same attenuation or impedance in common mode, while if we take a look to the differential mode, we see a complete different picture. So here the effect of the component with S, which is the sectional one, is where we are getting a really or a lowest symmetry of the component. Therefore, the effect in differential mode is much higher. So I talk right now about attenuation or impedance, and when I'm talking, I'm making no difference on both parameters. So basically they are the same. So the impedance is creating an attenuation in the line. The difference of the insertion losses or attenuation is that we are considering our complete system. If you go to our datasheet or to RedExpert, you will see that the graphs we are showing are measured at 50 ohm. So why is that? This has only an historical reason. So basically, early, or I would say 15, 20 years ago, they were not so easy to get a network analyzer. And getting one means that we could measure with basically 50 ohms impedance. Today, we have the possibility of changing the impedances of the network analyzer, and it's relatively easy without using any transformer. But in this case, we adopt this standard, and every manufacturer is using this 50 ohm standard. And what we offer, for example, right now as a service for our customers is RedExpert, where they can go and change the different impedances of the line and see how the choke will behave in their application. Also, beside RedExpert, we are implementing a new measurement setup with 4 ports where we can actually change independently the impedance of each port of our component through the usage of S parameters. So this is really useful if we are simulating or if we are creating simulation models. So if you are interested, you can find the S parameters in our website for some of the components. We are working on having all of them and creating new simulation models, so you can have more accurate data for your simulations. The rated current is also another parameter we are showing in our datasheet, and this is basically what I want you to understand here is the way we are measuring it. So the rated current is basically the temperature rise or the current we need to get some temperature rise in our component. In this case, we can see we get a temperature rise of 40 Kelvin with 1 amp. This 1 amp is flowing through both windings at the same time. So we don't have the current flowing only through one winding. We have both windings receiving the same current at the same time. So we get exactly the same data you will get in your application. So you will see the exact same temperature rise like we have in the lab. So what we give also extra to our chokes are not only the rated current, but the derating curve. This derating curve is important if you are using the choke over the maximum allowed or recommended ambient temperature. So if you get over this 70 degrees, you will need to reduce the rated current or the current you are applying to the choke. So you won't be able to apply anymore this 100% of the current. You will need to reduce, for example, if you are increasing the temperature to 90 degrees, you will need to use a maximum 80% of the rated current, which reduce also the heating on your component, which makes sure that you are not getting over this 125 degrees, which is the maximum recommended temperature to use the component. So finally, when we talk about saturation, or basically we are not talking about saturation when we talk about the chokes. So saturation is a parameter which is really has a big presence in the datasheet for power inductors, but we are not mentioning it for the chokes. And the reason is the field compensation. So here I showed you two graphs, and in one of the graphs, we see the attenuation or the saturation of the choke in differential mode up to 25 milliamps. And here we can see in differential mode, we have no saturation up to this liter current. And in common mode, the choke is saturating really fast. So if we set saturation is a 20% loss of inductance, we are already saturating with 5 milliamps. But this is not so shocking and shouldn't be so shocking because in common mode, we don't have such a high currents. So the currents we have in common mode are microamps. If we get to the milliamps in common mode, we have a huge common mode current, and we will have some unbalancing in the lines. We have some unbalancing of impedances in our system, which could be really, really dangerous in terms of other issues, not only EMC. So in this curve, we make a different experiment. We increase the current and we measure the differential mode current and the saturation of the choke. Here, we can take as an example the FC, a frame core choke we have, where the rated current of the choke, so which means we are rising already the temperature 55 Kelvin of the component at 0.6 amps. And we can see the curve is here on the top up to 4.5 amps. This is almost 8 times the rated current of the choke. So we are having some saturation effect at 4.5 amps while the rated current was 0.6. What we are seeing here is basically not saturation. What we are seeing here is we are getting the component is way too hot and it's getting over the 140, 150 degrees, which is already over our Curie temperature. And so we are losing all the magnetic properties of the core. And this is basically the effect we can see in this graph. So beside the common mode chokes, we have also differential mode filters or differential mode chokes. These differential mode chokes have different materials. What we have in our catalog are differential mode chokes made of iron powder and manganese zinc. And the relevant parameter are frequency characterization and impedance. So saturation and rated current are in this case also really important. But the two materials we are using here are, one of them is iron powder, which has an distributed air gap. so the saturation will be a soft saturation. And we have, for the manganese zinc, we have a rod core, and this rod core shows a huge air gap here between both ends of the inductor, which allow us to have a really high saturation of the choke. So now we talk about two different materials, so we expect to see some different in the impedance or inductance, and this is what we will also talk about later. Here we have the two inductors with the same inductance value, and we see at the beginning of the curve in the low frequency, we have basically the same impedance, which means same attenuation. But as soon as we increase the frequency, we see also that this curve change totally. So having almost 10 times more impedance in a manganese zinc core than in a iron powder. This is due to the losses we have in the core. We also need way more turns in an iron powder core than in a manganese zinc core, like we can see. So we have also different effects and different parameters of the core on the frequency. You can easily check all these effects on our ReadExpert module online. So choosing a component for a filter, let's go into detail in the moment we need to build a filter and what are the important parameters we need to consider. So allow me to start again with the common mode choke, so the central component of our filter. So when we check a common mode choke, usually what we get from customers or what you will see in some designs is so we need a common mode choke of 1 millihenry. So this 1 millihenry is only one indicator for the behavior of the choke in the low frequency. So remember, we were trying to include as much losses as possible in our circuit. So here, what I try to do is I compare 3 different chokes. 2 of them have the exact same material, but with different winding styles. And then another choke with also the same inductance value, but using another material. So the black curve is a curve with nanocrystalline core. So we can see the nanocrystalline core is showing a wider bandwidth, but lowest attenuation in some frequencies. So we get more attenuation in the highest frequencies, but less attenuation in the middle frequencies. Also a big bandwidth for this choke. If we consider also the manganese zinc material, we see at the low frequency all have similar attenuation or similar impedance, but as soon we increase, they are both changes. These two, the red and the gray curve, they stay the same up to a certain frequency, and then later on, this gray curve, which is belonging to this kind of component, to a frame core, where we have a very good defined winding chamber. This is the effect of reducing the capacitance between winding. This curve, the red one, belongs to this kind of components where we have more a wild winding, so it's not so controlled, and we have a highest capacitance between windings, so we cannot get such a wide band response, and we have a small drop, a pretty big drop in the maximum attenuation we can get with these chokes. So you can see here that 1 millihenry is not always 1 millihenry, so we have different behaviors of the choke depending on what we are looking. And the same for differential mode. So differential mode is basically about the parasitics. So it's showing a huge influence depending on the number of windings, the number of turns, the placement of the turns, the capacitance of the choke, the way we want it. So it's about the parasitics, and we can really not know without comparing. So the inductance will give us no tip or no indication about the differential mode attenuation. Last but not least, we have also to consider the rated voltage of our choke. This will be defined in some international standards, and this is basically the separation between both windings, which we are getting through these spacers in the middle. We have also here a small comparison. You can see here many different graphs. This is basically the impedance of a CMB component, and we are going from -40 degrees to 180. So This component is recommended only up to 125, so we will stay here more or less. But you see we get to a really high temperature. So when we check here, at 180 degrees, we basically lost all the magnetic properties. So which means we are over the Curie temperature, and the other curves are changing a lot. So we see some variations in the frequency. In the middle, with the temperature. So in the middle temperature, we have almost no change, or the change is not so drastical, but we can have really big variations at the end. This is totally changing if we have, for example, a nanocrystalline core. The nanocrystalline core is really stable with temperature, and the Curie temperature for a nanocrystalline core is over 600 degrees. So it's really difficult to reach, and we will melt the plastic probably before reaching the Curie temperature of this choke. So the variation or the deviation of the impedance and attenuation is really, this component is really stable in terms of temperature. When we include some white caps in our design, we said before that the white caps has a really big impact in the common mode attenuation. So we could think about increasing the white caps value and reducing the value of the choke. So we have not so much space taken from the design. But the problem with the white caps is basically that we have some leakage current. This leakage current is for some application really limited, and we also don't want too much current going to our ground. So it's also playing a little bit with these values and seeing where the limit for our application is. And this is the main effect of white caps. This definition of the leakage current is in the norm 60939, which is the norm, the standard for filters. So we have also in our portfolio a complete solution, including the chokes, including capacitors, X and Y capacitors, and this is basically the match code or the product family is CLFS. So we have different certifications, and for the design of this filter, we consider many different aspects. So first, we offer 3 different families or 3 different product, I would say, sizes. The smallest one is the single stage, where we include basically the schematic of the filter we were seeing until now. So 1 X capacitor, 1 common mode choke, and 2 Y capacitors. For the advanced single stage, we have 1 extra X capacitor to increase the effect on differential mode. And for the 2 stage, we include also another choke and another X capacitor, basically also to increase the common mode attenuation. When we got up to the design of these filters, we were thinking on the effects that could have increasing the rated current on the filter. So if we increase the rated current, basically if we use the same core material or the same size of the core, we will need to reduce the inductance value as the wire is getting bigger and taking more space. So we need to reduce the number of turns. This reduction of number of turns can be compensated with increasing the Y capacitors to increase also the effect in common mode of our attenuation up to a level. So we cannot totally compensate the lack of inductance or the lack of the losses generated by the core of the choke with the Y capacitors. The X capacitors are also increasing, basically to have also a higher effect in the differential mode signal. But the problem here is increasing the value of the X capacitor is also reducing the value of the bleeding resistor. The bleeding resistor will increase also the standby losses we have in our circuit, because there will be always some current flowing through this resistor. Even though when we define the X capacitor value, we are forced to have a fixed value of this bleeding resistor, as we need to discharge the capacitor. So our priority is not to kill our customers. So therefore, we try to keep this within the norm and allow the capacitor to discharge and not discharge on the user. So we made a small simulation of a filter, and this simulation was done with a signal filter. So why is that? Because basically in simulation of a signal filters, we could take an example with fixed impedances, and the calculation get I don't know if easier or complexer, but we have already some values which are fixed, and for this half an hour training, it was important to have some fixed values. So we basically talking with about an RS485 interface, and we have a maximum cable length of 1.2 kilometers in this standard. So 1.2 kilometers means we have a high efficiency antenna around 62.5 kilohertz. So we wanted to look for a common mode choke with already a good attenuation over at least at this 62.5 kilohertz. So the next important factor we needed to check was the attenuation in differential mode. So the attenuation in differential mode, we said that is basically the effect of the filter and the capacitance or the capacitors we have in differential mode. So we made the calculations with this standard, which has an impedance of each line of 60 ohms. So in differential mode, it's 120 ohms. And we look for a 3 dB maximum attenuation at 15 megahertz. So we allow the maximum energy of the signal come through the filter without being attenuated in differential mode. So with this basic data, we got the value of the maximum capacitance of the filter should be below 181.38 picofarad. If we check which capacitance we have in our system, they are basically the TVS diodes we include, and also the X capacitors and the X capacitors and the Y capacitors we have in our system. They all have an effect in differential mode signals. So at the end, we choose all the values, so we are below this 181. So we are getting 178 picofarads. If we get into the simulation more in details, we see that we can, the simulation was done with LTSpice. So also if you need some more information, we will be releasing one app note about this whole filter design. As soon as possible, let us know if you have interest, so we can we can send you the app note per email as soon as it's released. So we basically made the simulations in common mode here on the top and in differential mode on the bottom. And we compare these simulations values with the measured values. So we can see in differential mode, the values are pretty close to each other. In common mode, we have some difference from the calculation, but we are basically following the same curve. So we can say the curves we get compared to the simulation are pretty close one to another. So we have also another tools to work with this kind of to simulate or to test our filters. This would be our Design Your EMC Filter design kit. So this design kit allows us to build different filters and to test it in our application. So if we have the calculations or not, if we want to test some kind of filters, or if we have some default filter which is working for us, we can have it in this kind of PCBs, then build it into our application and test it how it's working. This Design Your EMC filter has basically all the components you need. Have the terminal blocks, the common mode choke, resistor and capacitors, and spacers, the PCBs. So there is a full range of components to build the filter. So how to destroy a filter? So what could generate that our filter is not working is basically the order of the filter. Are we filtering with the right order? Are we having enough attenuation in the rejection band? Do we have the right orientation of our filters? So if we have a high impedance on the line, we can start with a low impedance, which means a capacitor, or should we place the inductive components first? And also another big question we always have to ask ourselves is, are we filtering the right mode? So are we trying to filter differential mode with a common mode choke, or the other way around? Sometimes we see some people trying to replace common mode chokes with two different inductors. And we saw at the very beginning that the effect of an inductor, a single inductor or differential mode inductor, is the half of what we could expect in common mode. Saturation of the inductors, if we have differential mode inductors, they will be at some point saturating. So we need to take a look at which inductor are we choosing and that we are always below the saturation, so our calculations are as close as possible to the reality. So the CLFS has also some resonances as it is a real component. So we need to check also the parasitics in some frequency. If we start simulating with ideal components, we will see not so many parasitics or almost no parasitics. And this we need to consider, as the filter is not an ideal component, but what you are buying at the end is a real component. Dangerous location of the filter and also the input-output feedback. Like we see in this graph, it is really dangerous to have the input and the output of the filter in parallel. So if we have this kind of situation, we will have some inductive coupling here. So our signal noise or whatever signal we do have, instead of going through the filter, will jump from cable to cable. It will find a lowest impedance path here, avoiding the filter, which is a high impedance component. So try to place the filter as close as possible to the input, and always put the input and the output of the filter in series and not crossing or in parallel or close to each other. So the parasitics in the layout are really important. So when we draw a line in our system, we need to consider if it's a long cable, will be an inductance, and if we have in this long cable a capacitor connected, we have an inductor connected to a capacitor, which means we are reducing the efficiency of the capacitor. It doesn't matter if it's from the line to the capacitor or from the capacitor to ground. At the end, what we want to build between the line and the ground is with the capacitor a low impedance path, and placing an inductor or creating unintendedly an inductor in this line will be reducing the efficiency of the capacitor. And also one topic which we are not dealing a lot are the potting materials and the low cost equivalent. So basically, the expensive component in our chokes are the core material, the ferrite material. And this ferrite material could be also cheap or could be found really cheap in the market, but they will be affected by things like temperature or potting material. So if we have some potting material and we increase the temperature in our system, we could see that some pressure is created on the core, and this pressure could create a drop in the inductance. And if the pressure is so big, at the end we could break our core, creating a totally loss on the losses we are trying to generate in our circuit. So basically, these are the main point we need to consider while designing a filter. I hope you enjoyed this webinar, and I'm looking forward to reading some of your questions.
So thank you, Ismail, for this interesting and great webinar. As Ismail just mentioned, now we would like to turn our attention to your questions, and we wait a little until some questions have come in. Also, I want to mention that we now have a time of about 10 minutes in addition scheduled for this. So, Ismail, as I just saw the first question on slide 52, where do the differences between simulation and the measurement come from?
Well, always when we have differences in between measurements and simulation, like we can see, for example, in this slide, these differences are coming from the difference we can see in our parts. So when we simulate the choke, or when we simulate the different components, we take the average values, and as we have, for example, in the common mode choke, really huge inductances, the difference between the average value and the maximum and minimum values could be relatively high. We also have here the effect of the capacitors, and the connection of the capacitors, like we saw during the training or at the end of the training, could be not so close to the ideal connection in this case. So we try to get as close as possible, but we have always some parasitics on the traces. We have some reflections, which will change basically the response we got from the filter.
Okay, thank you, Ismail, for the explanation. Yeah, then we have a look at the other questions. So yeah, I saw the next question. Ismail, which tool are you using for the simulation?
So the tools we are using for the simulation is, in this case, is LTSpice. So you can get some information about LTSpice in our website. And we also have published, some time ago, we published a book about LTSpice. So you can get there also some really good tips about how to set up your circuits, how to prepare also the first simulations, and basically some leading for you for starting with this software if you didn't start already.
Okay. So the next question, for switching frequencies of DC-DC around 100 kilohertz, at which frequency appears the noise?
So what this is, if we have switching frequencies of in a DC-DC converter around 100 kilohertz, we will probably don't see the noise at this 100 kilohertz. We will have it, but we will see the different harmonics on our circuit. So we are starting for some tests. So I'm talking here about the widely used standard in industry. We are starting at 150 kilohertz. So we will probably see the first harmonic, or sorry, the second harmonic, third and fourth. So which are around 200, 300, 400. So at the end, these harmonics will be there. The question is if we get to attenuate them or if we are giving them a way out. So if we are facilitating the way for these harmonics to get out of our circuits, so to get back to the mains, we will see these harmonics during our EMC tests.
Okay. So yeah, I see the next question, also the derived. Ismail, shall we use a common mode choke for differential mode application in low frequency of 10 kilohertz?
So I don't know if I am understanding right here the question, because it could be two options. So I will explain both of them. So if you mean if we should use the common mode choke just to attenuate noise in differential mode around this 10 kilohertz, no, I don't think so. We don't have chokes which are attenuating at such a low frequency in differential mode. If with your question you mean that you have a differential mode application in low frequency where your signal or your delivered power is around 10 kilohertz, then yes, because we have, like I said, we have almost no effect in such a low frequency at 10 kilohertz in differential mode. But we have a lot of components, a lot of common mode chokes, which are already having a lot of attenuation at this 10 kilohertz. So the common mode choke is perfect, or is really good for attenuating already at this frequency, and it will have no effect in the differential mode noise or signal at this low frequency. So I don't know if I answered your question. So if not, please just place another question or try to let us know. This will be interesting.
So yeah, Ismail, thank you. Also the next question arrived. I hope I spell it right. Can X square Epsilon capacitors replace a centimeter choke?
Okay, I think that the right spelling is X2 or Y capacitors replace a common mode choke.
Okay.
So I'm afraid no, they can't. We can help to attenuate it. It's depending on what we wanna use and what are our targets. So if we really need a low a low attenuation, we can use only X and Y capacitors to get this attenuation we are looking for. But at the moment, we need a higher attenuation, or that the attenuation should be moved in a lowest frequency. We always need an inductor. So an inductor starts to have an effect in a lowest frequency than the capacitors, and we are able to get a much higher attenuation with just a common mode choke than with only capacitors.
Okay. Next question. What is your opinion about using ferrite materials for common mode chokes?
So my opinion, we basically need to use ferrite material for common mode chokes. So we are building only chokes with two materials. One will be ferrite materials, which are the family of manganese zinc, nickel zinc ferrites or ceramics. And we use also nanocrystalline material. These nanocrystalline material are metal materials. So these materials are basically having the same function of the ferrite material. So the reason for using ferrite materials is we get materials with a really high permeability. And what we want to reach with this high permeability is to have a lot of losses in the circuit. So increasing these losses will allow us to get a really high impedance and dissipate the noise we have in this frequency and also in lowest frequency. So we could have, actually we could create chokes with iron powder, I would say, but the effect of the iron powder or the losses we would be able to generate with this kind of chokes will be really low. So I think the right material to build chokes is ferrite. So I'm not 100% sure if I answer your question. I hope yes.
Yeah, if there are some questions left, we will also you're also able to write them afterwards at isus-webinar@we-online.com. So Ismail, last question. Sometime we are using ferrite bead in place of inductor because we know the impedance level of ferrite bead, but in inductor we have only inductor value. So how can we get the impedance value of particular inductor?
Well, we are now working into adding the impedance value of all of our inductors in the datasheet. You would be able also to request the impedance graph of any inductor to our hotline. So, or through the chat. So you can go to our website and contact our colleagues and ask them about the impedance value of any inductor. And you are also able to get this impedance value with any simulation software. So we have all the models of our inductors. We have it online for LT-SPICE. We have it also for P-SPICE. So basically for all the SPICE-based simulation softwares. So you are able to get this impedance either with a simple simulation, or you can, if you cannot find this in the datasheet, you can also contact us through our hotline or the chat function in our website, and we will provide you the impedance graphs of the inductors.
So many thanks, Ismail, for the explanation. And now we are finished with our webinar. As mentioned, if there are any questions left, we will answer them via email afterwards. And also you have the opportunity to send your questions to our email. Thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Ismail, for this interesting and great webinar. I hope.
So thank you. Oh, sorry.
No problem. I hope we will hear us at our next webinar, and I wish you a good day. Goodbye.
So thank you very much, everybody, for attending, and thank you also, Marcos, for moderating this webinar. So have a nice day and stay healthy.